Welcome back. In this video, we'll consider an example of the calculation of residue and we'll see exactly how it works in some questions. Now, as always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. Now, for the first question, we have to find the residue of f of z equals z raised to power z divided by z minus a cubed. Now, if this is the case, the very first thing, as always, is to find the poles. So we'll set the denominator to 0. Now, this shows us that z equal to a is a pole of order 3. This is good. Now, as always, before we even look at setting the denominator to 0, it is common practice or it is due diligence to also look at the function and see if some things cancel out before you go through. For instance, if there was a z squared into z minus a cubed, then z could have cancelled something there and then your question would have simplified further. So you only move on to setting the denominator to 0 when you have fully verified that there is no part of the function that can cut out. Now that we have found the pole, the next thing for us to do is just to simply take the formula. Now, in this case, the residue is f of z, right, at z equal to a. In this case, would simply be 1 over the formula, which would adapt based off the parameters we have, 1 divided by 3 minus 1 factorial, limit as z tends to a of the second differential, in this case, of z minus a cube, z e raised to the power of z divided by z minus a cube. So this cancels out the pole. So from here we have 1 over 2 limit as z tends to a, the second differential of z e raised to the power of z. Now, of course, this is going to give us a product rule from first evaluation. So you have 1 over 2 limit as z tends to a, the differential of this product rule, which would simply be z e raised to the power z plus e raised to the power z by product rule. Now, from here, we differentiate one more time. So you have limit as z tends to a of z e raised to the power z plus e raised to the power z plus e raised to the power z. Right? So because this differential will be a product rule and the differential raised to the power z remains the same. So from here, we see that this would evaluate into 1 over 2 limit as z tends to a of z plus 2 e raised to the power of z. That's what we're going to have. So if we evaluate this, we can see that therefore the residue of f of z as z equals a or tends to a would simply be 1 over 2 a plus 2 e raised to the power of a. And this is going to be the evaluation of the residue. So we see that from here on is just basic computation using the formula. Not so much time spent there. Now, we move on to the next question, which is this one. For this one, let f of z, as always, be equal to e raised to the power iz divided by z squared plus a squared. Now, from here, nothing cancels out, so we set the denominator to 0. So from here, we see that this would give us complex roots because we have z squared equals minus a squared. So if we take the square root of both sides, what we are going to end up having is z is equal to plus or minus ai. Now, if we have plus or minus ai, how exactly can we proceed from here? It means that we would have z equal to ai as a simple pole, and then we will also have z equal to minus ai as also a simple pole. Now we can evaluate the residue at both of them. Now we'll take the first one. The residue of f of z at z equal to ai would simply be limit as z tends to ai of z minus ai e raised to the power iz divided by z squared plus a squared. Now we cannot evaluate as it is because if we do, and put the limit in, the denominator would go to 0, and we will then have ourselves an undefined function to deal with. So what do? We simplify it a bit. So you have z minus ai here, and then this would rewrite into e raised to power iz, then divided all through by z plus ai, z minus ai, because this is what it splits into. Remember that what you have here is simply difference of two squares in the complex case, right? Because you know that if you have z squared plus a squared is the same thing as saying z squared minus a squared I squared, right? So it is difference of two squares. So you have z plus ai, z minus ai. Now, good. From here, we see that the residue of f of z at z equal to ai would simply be, this will have vanished and you'll be left with these two. You'll be left with e raised to the power of iai divided by ai plus ai. And then from the top, we see that we'll have I squared, so that's minus a. And so we can evaluate this as e raised to the power minus a divided by 2ai. Now, if you are not comfortable leaving the denominator with the complex variable I, then we can rationalize, and rationalizing would give us minus I raised to power minus a divided by 2a. This will be the residue at z equal to ai. That is the first one, at z equal to ai. The next thing for us to do is to find the residue at z equal to minus ai. Now you can take a pause to try an attempt and find that residue, then compare with the answer we're going to get shortly. And then you can also check through this if you fully understand the rationalization that has happened here. That just implies us multiplying by I divided by I, so it balances out. Now let's continue. From here, we see that the residue at the second point, as f of z at z equal to minus ai, that's at the second pole, we see that the evaluation of this residue would send it to have limit as z tends to minus ai, and then z plus ai e raised to the power of iz divided by z squared plus a squared. So the same thing would happen. We'll have limit as z tends to minus ai, z plus ai e raised to the power iz divided by z plus ai, z minus ai. So this cancels, and then when we evaluate, we are going to have e raised to the power minus iai, and then at the denominator, we are simply going to have minus ai minus ai. So the top evaluates, I squared is minus 1, so evaluates to e raised to the power a divided by minus 2ai. Then if we decide to rationalize, it means that the residue at z equal to minus ai would simply be I e raised to the power a divided by 2a. This is what we're going to have. And that's because the negative from the multiplication of I divided by I, which would have been I squared at the bottom, that would cancel the minus, and then I comes at the top. So we have found the residue at z equal to ai, and we have found the residue at z equal to minus ai. So this shows us how to find the residue, multiple residues within the questions, as always. Now, what you would also notice is, assuming that we were finding the integral of a by iz divided by z squared plus ai squared plus a squared. In that case, we had found the residues are based off the region that would be provided. We just have simply added them and multiplied by 2 pi I. This is what we are going to be looking at in great detail in the next bit of our videos. We are going to look at how to evaluate integrals, and we will be considering two major clarifications to it. We would consider the evaluation of the indefinite integral, which is, of course, just find the residues, sum them together, and then multiply by 2 pi I, provided the region or the contour is satisfied. Then from there, we would also now look at the evaluation of the integral in the definite case, the evaluation of the definite integral. In that regard, we evaluate the unit circle, as well as the semicircular contour. So we have this very, very important concept to look at, right? This, of course, we are getting very, very close to the conclusion of this phase of the complex analysis playlist, right? Which, of course, would draw the curtain at the end of the integral series, which we have gotten into now. But then we would also have more complex analysis concepts coming up, right? While we also begin to add in concepts in other courses as well. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.